Section 5.3, Solving Trigonometric Equations. This section is going to step away a little bit from identities that we have focused on in the first couple of sections. A lot of this section is going to build upon what we covered in Chapter 4. We're going to need to use our All Students Take Calculus acronym to determine where we're going to draw reference triangles, and you'll see the relationship between what we're going to do in solving trig equations here with what we've already covered in Chapter 4. First thing, when we're solving a trig equation, instead of getting just the variable x by itself, our goal is to get the trig function by itself. So in this case, we want to solve for sine x. So I'm going to add the 1 over to the other side, divide by 2, and we get sine x equals 1/2. From here, we need to go back to our reference triangles. Where does sine equal 1/2 at? All Students Take Calculus tells us that sine is positive in quadrants 1 and 2. So we're going to draw a reference triangle in each one of those two quadrants. Sine we know relates opposite over hypotenuse. Should recognize this triangle as being a 30, 60, 90 triangle. So the bottom side here is going to be root 3 and negative root 3. From here, our reference angle should be identifiable. We know the smallest side is across from the smallest angle, so this is 30 degrees, and this is 30 degrees. So our two solutions, when does sine equal 1/2? First rotation is 30 degrees. Our second rotation, we know it's 180 if we go halfway around. 30 less than that is 150 degrees. Those are our two solutions between 0 and 2 pi. In other words, those are the only two spots that sine is positive in one complete revolution. If we did this in radians, that would be pi over 6 and 5 pi over 6. Now, we're not yet done with this problem because there is no domain restriction placed upon this. In other words, in a lot of the problems you do, in most of them that you're going to do, it will say something like solve on the interval from, let's say, 0 to 2 pi, which means then that you would only be finding your solutions between 0 and 2 pi. 30 degrees, 150 degrees, or pi over 6 and 5 pi over 6 would be your only two solutions. In this case, though, we did not have that domain restriction, which means we need to find what is called the general solution. We know that the general or standard period of a sine function is 2 pi radians. So what we need to do is take each one of these solutions, pi over 6 and 5 pi over 6, and we need to add to it that period because we know that the function keeps repeating itself after 2 pi radians. If you think back to when we were graphing, we graphed one full period and then we knew all the other periods would look exactly the same because it just repeats itself over and over again. So to this, we need to add 2 pi times n. To this one, we need to add 2 pi times n. In other words, if I add 2 pi to this first one, 13 pi over 6 is also going to be a solution. Add another 2 pi. 25 pi over 6 is going to be a solution. Add 2 pi to 5 pi over 6. 17 pi over 6 is going to be a solution. Add 2 more pi and so on. In other words, n here represents the number of rotations we would make within the coordinate plane. In other words, if we revolve one more time around, 1 times 2 pi, we add 2 pi, 13 pi over 6 is also a solution. If I revolve around 2 more times or go 2 revolutions, now I'm adding 4 pi. That gets us to our next solution. So there are infinitely many solutions to these trig equations if there's not a domain restriction given up here in the beginning of the problem. Most of the time you're going to have a domain restriction. These first two we are not going to. So number 2. Sub-goal in solving, get the trig function by itself. So just like in regular equations, we want to get everything with a variable to one side, everything that doesn't to the other. When it's trig functions, we want to get all the trig functions together. So I'm going to add the sine x over. I'm going to subtract the root 2 over to the other side. Finish solving. We get sine x equals negative root 2 over 2. So now when we go to draw our reference triangles for this one, We want to know when is sine negative. All students take calculus, tells us that sine is negative in quadrants 3 and 4. We need to derationalize this value or it's not going to be a triangle that you recognize. Remember, we derationalize by multiplying by the radical over itself. Negative 1 over root 2. When we simplify, opposite over hypotenuse. Third side then, from your, again, this time 45, 45, 90 triangles are going to be 1 and negative 1. So from that, you should recognize this reference angle to be 45 degrees. So when does sine x equal negative root 2 over 2? First rotation takes us to right there, which is 225 degrees, or 5 pi over 4 in radians. Our second rotation, all the way around there, 360 minus 45 is 315 degrees, or 7 pi over 4. That would represent our solutions in both degrees and radians if, again, we had a domain restriction where we were only talking about x values between 0 and 2 pi or 0 and 360. In this case, we don't have that restriction, so we need to go a step further and, again, give the general solution. Our general solution, 5 pi over 4. Sine repeats itself after 2 pi radians times the number of revolutions we want to take, and 7 pi over 4 plus 2 pi n. Number 3, now we do have that domain restriction here. 3 tangent squared x equals minus 1 equals 0, and we're solving only for solutions between 0 and 2 pi. Begin the same way. We want to get tangent x by itself. So tangent squared x, add the 1 over, divide by 3. Finish solving for tangent by taking the square root of both sides, and we get tangent x equals plus or minus 1 over root 3. So here when we go to draw our reference triangles, we're talking about tangent being positive and negative. Well, we know tangent is positive in 1 and 3, negative in 2 and 4, which means we're going to have reference angles in all 4 quadrants. One and 3 is where tangent is positive. 2 and 4 is where tangent is negative. Tangent now is opposite over adjacent. So 1, 1, negative 1, negative 1. Adjacent is root 3 and negative root 3. Hypotenuse, recognize this as being a 30, 60, 90 triangle. Reference angle in all 4 reference triangles is going to be pi over 6. We're told to find solutions between 0 and 2 pi, so we know our solutions need to be in radians. We have 4 different revolutions here to look at. First one is pi over 6. Second one, 5 pi over 6. Third one, 7 pi over 6. And the fourth one, going all the way around here, 11 pi over 6. We do not need to worry about adding the period of the tangent function to these because we are only finding the solutions between 0 and 2 pi. Example 4. If we get everything on one side of the equation here, we end up with cotangent x cosine squared x minus 2 cotangent x equals 0. We're trying to solve. We can factor out a cotangent x out of everything here. So we have cotangent x times cosine squared x minus 2 equals 0. Once we have a factored equation that's set equal to 0, we can set each factor equal to 0 and continue solving. Cotangent equals 0. Cosine squared minus 2 equals 0. First factor already is solved. Second one, cosine squared x equals 2. Take the square root. Cosine equals plus or minus root 2. From here, cotangent x equals 0. Need to draw reference triangles. Remember, when tangent or cotangent is 0 or undefined, we are talking about quadrantal angles. We know that cotangent is the same thing as cosine x over sine x. So if cotangent is going to be 0, that means that cosine has to be 0. So on our quadrantal angles, where is cosine 0? Remember, cosine is the x-coordinate. Cosine is 0 up at pi over 2 and down at negative or positive 3 pi over 2. So the two solutions we get from here are pi over 2 and 3 pi over 2. From our second factor, cosine x equals plus or minus root 2. We know that we would have reference triangles drawn in all four quadrants. However, when I look at this, cosine we know is adjacent over hypotenuse. That can't happen. The reason that can't happen, we cannot have a leg greater than the hypotenuse. So from this factor, there are no solutions. So we don't need to worry about that. Our two solutions to this equation are pi over 2 and 3 pi over 2. If you remember back when we graphed cosine functions, remember cosine values fluctuate between negative 1 and 1. They never get up to root 2 or down to negative root 2. Last example here, we have a trinomial. Anytime we have a trinomial, remember that's a quadratic equation. We can factor or use the quadratic formula. Factoring obviously is the quickest way. This does factor 2 sine x plus 1 times sine x minus 1. We can set each one of those factors then equal to 0. 2 sine x plus 1 equals 0. Sine x minus 1 equals 0. Solve each one. We get sine x equals negative 1/2. And we get sine x equals 1. Take each one individually, starting with the first factor. Sine x equals negative 1/2. Draw your reference triangles. Sine is negative. All students take calculus in quadrants 3 and 4. Opposite over hypotenuse. Recognize that reference triangle as a 30, 60, 90 reference triangle. Reference angle that we're interested in is pi over 6. So our two solutions we get from the first factor, this rotation here, which is 7 pi over 6. That rotation there, which is 11 pi over 6. There's our first two solutions. Second two solutions come from our second factor, sine equals 1. Remember, when sine or cosine is 1, 0, or negative 1, again, we're talking about quadrantal angles. In this case, sine is 1. We know sine is the y-coordinate of our quadrantal angles, whereas sine equal to 1, right up here at the ordered pair 0, 1, which is pi over 2. So we have three solutions.